So once more, I will tell you tonight about computation, on particularly square root optimization in C on Fortran, not C++. If it were in C++, I would have been lucky to use Eve, but I started this optimization with the help of Pierre a long time ago. So I will briefly introduce the point with a physics case. Our colleagues in the Agatha nuclear physics experiment have a problem called the pulse shape analysis. Their detector are measuring some signal over time in many segments of the same detector. Given each of these signals, they want to fit it to the red dotted line that you see here. And to see the quality of the fit, they are using this chi to the p huge, ugly formula. So the statistically inclined among you will recognize the chi-square, but here it's a chi to the power p, because they couldn't satisfy with the p equal to. And in particular, okay, so here we have a better signal, it fits better. And they decided, they simulated that p equals 0.3 was the best value to reproduce their fit. Okay, so 0.3, it's a good number for us human. It's a bad number for the computer, as it has no binary exact representation. But so what? It's an algebraic function with integer coefficient polynomial roots. Of course, we could naively express it as the exponential of 0.3 times log of x, using not only the error on 0.3, but two elementary transcendental functions. So this is costly. And this was written a long time ago, before the MATLib 2.41 was out with correct rounding. So it was not guaranteed. And it will not be guaranteed before a lot of time pass on that all machine adapts to this new libc. So you have already seen the tables maker dilemma. As for the lookup table that the physicists chose to use to improve the speed of their evaluation, they decided to convert the argument of their power 0.3 to an integer first, then return a table value t indexed with this integer. So it was a huge continuity loss, and as such a big accuracy loss, mostly for a small value of x. It took a huge memory footprint of 2 megabytes. And the worst was that they stored not only the positive argument, but also the negative argument. And when you take this power of the absolute value, it has no effect. So they doubled the memory footprint to no avail. What is more, when you look in a lookup table, this is an indirection. So it's impossible to vectorize, whereas the computation for p equal to, they had vectorized it with intrinsic. So all the things you don't want to do, particularly when you see here that, okay, the L3 cache has 8 megabytes, but all the other cache will suffer a lot from this huge lookup table. Okay, so what alternative evaluation do we have? We can use the famous power function for float, hence the f. We could use the not so nice XPEF of log f. We could win some time using the exponential in base 2 with the logarithm in base 2. We could use the cube root if we are ready to say that 0.3 is not far from 1/3. And we could also design our own root. So let us start with the cube root. The physicists agreed for this small change of the value of p. It was negligible. Okay, so how would we proceed to evaluate the cube root? It's an algebraic function. First, it exists in the libm, so it's always nice when we can use existing libraries. But by the way, how would you extract a cube root? Any idea? Okay, so when we want to extract a root, we have some function, and we are looking for the zero of this function. And the classical method is Newton. You start with a not too bad guess of your root, and you improve your guess with these kinds of steps. And at this time, they had no CPU, no GPU, and his friend LA went further with a more complicated method. So the nice point about the LA method compared to the Newton method is the Newton method is quadratic. If you have one good digit at step 1, you have 2 good digits at step 2, and 4 at step 3. And for LA, it's cubic. So 1 good digit means 3 good digits at the next step and 9 at the next one. So, okay, it costs more, but why not? Okay, so even before we implement the cube root, how will we compute the square root? It exists on our calculators for 50 years. What does it do? Okay, so we have the famed method of Aaron of Alexandria. You have some hypothesis at the nth step, and you try to find the average size of the corresponding rectangle. So here is the half perimeter on top, and you divide it by 2. And by the way, how do we divide? So we have the Newton method that we can implement in this way to compute the inverse of a number. And if you rescale things properly, you can compute a division using only multiplication and repeating. And in fact, the famed Doom algorithm computes the inverse square root with no division, but only with product this way. And once you have the inverse square root, you multiply by the number, and you have the square root. So you don't need any division. Okay, so now for the cube root of interest, Newton would give us this formula, and LA this formula, so almost as difficult to evaluate. Let's go for LA. Okay, so I already introduced the floating point formats. And the next problem, now that we have the iteration in place, is how to reduce the study interval. I mean, how will we get a nice starting point for these iterations? So you can see that as the number that we have seen here have their exponent as a power of 2, they are expressed as a power of 2, you can check if the exponent is a multiple of 3, a multiple of 3 plus 1, or a multiple of 3 plus 2. And so you only need to evaluate your cube root between 1/8 and 1. So we have limited the study interval, and we use a Chebyshev polynomial using the REMEZ algorithm to get the coefficient of this polynomial. And we, of course, express it using Horner-Ruffini method, and very likely using FMA, as you can see here, a product on the sum in the same group. And okay, the starting point is graphed here, is plotted here. And you can see that it's very difficult to see the difference between our polynomial, between 1/8 and 1, and the exact formula. So when you look at the relative discrepancy, you see that thanks to the REMEZ algorithm, we have minimax. The extrema are exactly at the same distance, alternating from minus to plus, and we have a very small relative discrepancy. So let's code this, and we start in C. As we will see, this is the easiest way to get things to vectorize. Well, except if. So here there is this extraction from the number, from the absolute value of the number that we want to take the cube root of. We extract the mantissa in B and the exponent in E. So the three next line are something else. And then we rescale B according to this new exponent, S. And we apply here the FMA for float, for single precision, with the value expressed exactly as they are in the binary representation. Okay, I started with a double. So the first part of the computation use only floats, and then I go to the double version because the number of digits will be improved by the Ailey iteration that you see on this line. So here is the second one. Okay, so in principle, we could vectorize it using the pragma OMP declare SIMD for the function, and everything would go nicely. And then in our program, we would call this myCBRTF function on the array, and we could display the time spent on this. So in this case, when we use it in a scalar way, and later when we use it with the vectorial corresponding function, myvecCBRTF. Okay? Well, maybe we have to help the compiler. We should provide options. So optimization, specify what kind of hardware we have. Maybe also say what kind of AVX vectorization instruction we have. I've been referring to OpenMP pragma, so OpenMP SIMD. And I tell him to vectorize and to provide me information about what kind of optimization are done. And to be verbose about the vectorizer. Okay, so minus G will help getting the line number when we use Macao, because we will use Macao. So is it enough? Does it work like this? Only providing OpenMP directives on compiling. So we look at the object dump, asking for disassembly, and we see a lot of V. So maybe it has been vectorized, but in fact, no. No, because we have scalar and not packed instruction. What is more, we wanted AVX2, and we see that the registers are only XMM, which is not a good news. So let's use Macao, even if it's not so good for the morale of the troop. Okay, so here the results are given with the latest Macao version on the version that in the end succeeded to compile. I did not show the bad news that one gets. So with AVX 512, okay, I should have shown you the version with AVX2, but AVX 512 is a bit more difficult. And this is AVX2. So now this time, with the expert Macao report, we see that we have YMM in AVX2, and we have packed the PS vector instruction. So it's better. So where was the problem? Because we didn't see what changed from the initial version to the last version. Okay, so in this point here, you see that we extract the fraction FR on the exponent from a floating point number. On doing so, we have a function that returns two arguments, which is maybe not easy to vectorize for the compiler. And another point that I have learned yesterday, thank you, Joël, is that this frexp instruction function is modifying Erno, the infamous Erno of the C library. So maybe I should have used fnomat Erno, which is an optimization I didn't know, that for mathematical function will consider that you will not look at the result, because with floating point number, with IEEE floating point number, you always can check if the result is none. You don't need this Erno on top of this. Okay, so what I did to replace this frexp was to do it the dirty way, because I know the representation of IEEE number. And this is a good point of this standard, because for almost 40 years, all the floating point number have been following on most machines this format. So here, I don't show you the dirty bit handling things, but you can find it at on the URL at the top. Okay, so it shows us that the floating point are a leaky abstraction, and hopefully we have a standardized interface for extracting the component, extracting the member of the floating point object, changing. So you can see the frexp as a getter and the loadexp as a setter. In this respect, Fortran provides two different functions, so it should be better, but we will see. And in the end, we had the following result. The POF function is in fact rather accurate, but it takes really a lot of time. They compute in double precision. So, okay, this array is for the double precision version. PO is in fact computing with 61 bits of accuracy, even for doubles which have only 53 bits. The Intel compiler is 10 times faster on POF. The typical way to express things is very well vectorized by GCC, and it was already 3 years ago. ICC is even better. We can win a small 10% with log2 basis. On the cube root of the libm takes almost as much time as POF. So it's quite surprising because it should be very easy to evaluate it. So when we compare this CBRTF of the libm to ours, in fact, we see that the vectorized version is way faster than the vectorized version of the libm. 2 years ago, so 3 years ago, so your mileage may vary. Okay, so speed is one good thing, but what about the accuracy? So here also, it's the double and not the float version. So when you design unit tests with mathematical functions, you have the problem. I want to check that my function has a good result, but how should I compare the value? Besides comparing two floats, which is always difficult. So even if you don't know what value you expect for the cube root, what you expect are two simple things. The cube root of the cube should be the value, and the cube of the cube root should also be the value. So let's compare in which case we don't have this equality with random number, 10,000 random number. And in these cases, okay, the first test pass 57, is not verified in 57% of the case, the second in 83% of the cases. So the cube root of the libm was really bad. So I've just given a try to the 241. Now it's perfect. It's as good as the one that I've been describing today. And in fact, even this horrible way to express it was way better than the implementation of the old libm. Okay, so now for the implementation of today. So this first test has no error because with multiplication, you will be very accurate, and then the cube root will provide a result with less than 1/3 of machine epsilon of error. Whereas if you first take the cube root, you will introduce half an epsilon of error, and the cube will make it 3/2 of an epsilon machine. So you may have a small discrepancy at the level of half machine epsilon, which occurs in 2 cases in 3. So not too bad, and better than the other solutions. Okay, so as I could do it with a third root, and let's do it with a fifth root. And the reason to do so is because the power 3 to the 3/10 of something is the fifth root times the square root of the fifth root. So we compute the REMEZ algorithm, and the value are even better than for the cube root. Okay, so I don't enter the detail of the REMEZ algorithm, but when you want to evaluate a new function, it will be helpful. And then the LA iteration, when instead of m equals 3, you have the general m, in this case, m equals 5, you have a sensitive way to express things. So in the numerator, one addition for multiplication. Same thing goes in the denominator. You have an extra division on multiplication. So in total, 12 operations with rounding, but as you are with positive numbers, you have no catastrophic cancellation. So this algorithm is quite stable and will introduce 6 machine epsilon in the worst case, an error which is okay, under control. For the record, the cube root we just had before would introduce, in the worst case, 4 machine epsilon. So in fact, we see that they are not so the worst case error is almost never met. Yes, why do I take the 5th root, then the square root of the 5th root? Because when you want to evaluate the 10th root, that I would then have to cube, the numerator make in total 16 operations, 8 machine epsilon worst case error. So the benefit is not here. What is more, the convergence of this polynomial for the 10th root requires a lot of degree to have any kind of accuracy. Okay, so can we do it now in Fortran? So you can exercise starting with this URL on top. As any good exercise in this school, you will find in this repository not only the attempt at vectorizing the cube root, but you should start with the attempt at vectorizing an Hadamard product in Fortran. As a conclusion, we should not only optimize matrix product, okay, the libraries are here, and I've done this work for us for a long time, but you have a lot of dedicated functions in your field that await for you to bravely vectorize them. If they are on the critical path in the innermost loop, be it whatever, zeta function, Bessel function, spherical Bessel function, you name it. To do so efficiently, you have to do a lot of tests of speed and accuracy. So you have to design all this set of tests. You have to practice perf on Cana that I have no time to detail here. Give a try to contemporary vectorization if you are not in C++ and cannot capitalize on the work of Eve. It's a bit difficult. OpenMP SIMD does not work by itself. You have to check that your compilers vectorize properly. So be proficient in Macao. It turns out that the floating types are better used as objects than most objects people construct. People feel compelled to get the getters and setters. So with float, almost nobody uses accessor except to build new method, as was shown here. And of course, don't forget to call your favorite developers when it comes to computation, but also when it comes to tool. These computations have been made by professionals. Try this at home. That's it.